1970. Before there was an OSHA inspector, before there was a safety poster bolted to the wall, an American worker died on the job every 38 minutes. Not every week, not every day, every 38 minutes, around the clock, 3 shifts a day, 6 days a week. 14,000 dead in a single year, 2.5 million more hurt badly enough to be pulled off the line. The machines never slowed down to let anybody catch their breath. 600-ton stamping presses breathing hydraulic fluid like it was blood. Rolling mills that could flatten a red-hot steel ingot the length of a school bus into ribbon in under a minute. Overhead cranes lifting loads heavier than houses on a cable no thicker than a man's wrist. Conveyor lines running bucket after bucket of grain or ore or coal 20 hours a day through tunnels nobody outside the plant ever saw. Engines the size of a garage, turning shafts that could take an arm off before a man even understood what had happened to him. Call them what they actually were. Beasts on a leash, every one of them, and the leash was only as strong as the last person who'd bothered to check it. A single automotive stamping plant might run a dozen presses like that one under a single roof, each striking a sheet of steel with enough tonnage to fold a car door in one stroke, 15 or 20 times a minute, hour after hour, 3 shifts a day. Walk the floor of any of these plants at 3 in the morning and you'd feel it before you understood it. The ground itself humming underfoot from a rolling mill 3 buildings over, the air thick with the smell of hot grease and cutting oil. 100 small machines all breathing in a rhythm nobody had ever bothered to write down. Here's what almost nobody outside a factory floor knows. The single most dangerous part on most of these machines usually isn't the blade, or the ram, or the 2,000-degree furnace. It's a bearing, a ring of hardened steel, smaller than a dinner plate, packed with grease, spinning a few thousand times a minute in a spot where nobody's looking. Starve it of lubrication for a few weeks and it will fail, quietly, then catastrophically, and sometimes fatally, and it can do all 3 in a matter of seconds. American factories built the biggest, most powerful machines the world had ever seen, and for most of a century they ran them the way you'd run a car with no oil light. Drive it until it seizes, then fix it. Japan looked at that same problem and answered it with something almost embarrassingly simple. A new set of eyes, trained on a part of the machine nobody had ever been paid to watch. It turned out to be the entire difference between a factory that buried its own men and one that didn't. What was it? And why did it take American industry the better part of 2 decades to swallow its pride and copy it? The bearing that cost $40. Start with the smallest one, Hayesville, Kansas. A grain elevator run by a company called DeBruce Grain. A 9-story concrete tower packed with wheat and milo dust so thick that on a bad day, workers said they couldn't see their own hand in front of their face. Deep inside it, on an ordinary morning in June, one bearing on one conveyor roller had gone dry. Nobody had greased it in time. It seized solid. The belt above it kept running anyway, dragging itself across the frozen roller thousands of times a minute, the way a boot heel drags across the rough strip of a matchbook, until the metal underneath got hot enough to set the surrounding dust on fire. 7 people died. 10 more were hurt. The bearing itself, brand new, cost about $40. Now go back 21 years earlier to a bend in the Mississippi River just outside New Orleans, a town called West Wego. 3 days before Christmas, 1977, workers were stopping by a grain elevator to collect the turkeys their company was handing out as a holiday gift. Some of them weren't even on shift that day. Just before noon, the whole structure came apart at once. A fireball rolling 100 feet into the air. A 250-foot concrete tower folding sideways directly onto the 2-story office building next door, where the paperwork got done and the turkeys were being handed out. 36 people did not go home that week. It remains, to this day, the deadliest grain dust explosion in American history. 2 disasters, 21 years apart, in an industry that had already had the answer to both of them sitting on a shelf for over a decade by the time the second one happened. Maintenance itself, the studies would later show, was quietly eating somewhere between 15 and 40% of a factory's entire production budget, year after year, largely because so much of it was spent reacting to emergencies instead of preventing them. Nobody wrote that number on a wall. It simply vanished into overtime pay, expedited parts shipments, and scrapped product, one unplanned breakdown at a time. Here's a number that sounds boring until you understand what it actually means. For most of the 20th century, the average American factory ran its equipment at somewhere between 40 and 60% effectiveness, a measure engineers eventually gave a name, overall equipment effectiveness, or OEE, not 40 to 60% uptime, effectiveness. That means on your best machine, on your best day, close to half of its theoretical output was quietly bleeding away into jams, breakdowns, slow cycles, and scrapped product, and almost nobody on the floor could tell you exactly where it had gone. A rolling mill that should have run around the clock sat idle, waiting on a spare part that was 6 weeks out. A press that should have stamped out 1,000 pieces an hour, lost 20 minutes here and 30 there, to a jam nobody had bothered to diagnose, even after it happened for the 5th time that month. And here's the fact that should embarrass an entire century of American engineering pride. The country that put a man on the moon, that built the interstate highway system, that poured out more steel than any nation in recorded history, took until the middle of the 1980s to formally borrow a maintenance philosophy from a Japanese auto parts supplier most Americans had never heard of. A philosophy that required no new dollar of equipment to start working, only teaching the person already standing at the machine, the operator, to actually look at it differently. That's the whole secret. It sounds too small to matter. It is not. 30 seconds of a worker's attention that never happened is the entire distance between an ordinary Tuesday and Hayesville, Kansas. We're going to get to exactly what that trick was, exactly how it worked on a mechanical level, and exactly why it took corporate America 20 years to swallow its pride and copy it. But first you need to understand the world it was walking into, because in 1970 alone, unguarded punch presses and power shears took hands and arms off American workers by the thousands, with no cage, no light curtain, nothing standing between a set of fingers and a slide of hardened steel coming down with several tons of force behind it. Federal safety investigators would later trace that same pattern of injury across power press brakes, roll-forming machines, printing presses, mechanical shears, grinders, and slitters, an entire family of equipment that shared one thing in common: a point of operation where two pieces of hardened steel came together fast enough to end a career before the worker even finished exhaling. Hold all of that at once for a second. A death every 38 minutes, equipment running at barely half its own potential, a $40 bearing capable of killing 7 people in the time it takes to boil water, and a fix that had already existed, fully documented, for years before Kansas ever had reason to hear about it. What was the fix? Why didn't every plant already have it? And why did a country obsessed with horsepower need 2 whole decades to realize horsepower was never going to be the answer? The nation that ran machines into the ground. Nobody was listening to the machines, and for most of the 20th century, it was going to cost American workers their limbs, and sometimes their lives, before a single person in charge admitted it. Through decade after decade, a factory's maintenance department existed for one purpose only: to show up after something had already broken. That was the job, not prevention. Response. Engineers eventually called it run to failure, though nobody used that phrase out loud on the floor. It was simply how a shop worked. A press jammed, a bell rang somewhere, and a crew of 2 or 3 men in gray coveralls dropped whatever they were doing and ran toward the smoke. If a bearing had been squealing for 3 weeks before it finally seized, that squeal was somebody else's problem, because the men who could have heard it The operators, standing right next to the machine for 8 or 10 hours a day, were never asked to listen. Their job was output. Somebody else's job, in theory, was keeping the machine alive. Walk that habit through the steel mills of Pittsburgh, the auto plants ringing Detroit, and the grain elevators strung along the Mississippi, and you'd find the same basic arrangement everywhere, dressed in different overalls. A machine ran until it complained loudly enough to stop the whole line, and only then did anyone with the authority to fix it get involved. Nobody was measuring the 4 quiet warnings a machine gives off before that point, because nobody had ever been assigned to measure them. That division of labor was baked into American manufacturing almost from its founding, and on paper it made a certain kind of sense. Divide the work. Let the specialist specialize. But it built a blind spot the size of an aircraft hangar, because the person standing closest to a machine's daily behavior, its normal hum, its normal heat, the particular way its normal vibration felt through the soles of his boots, had no training and no mandate to say when something felt wrong. By the time a maintenance crew finally arrived, wrong had usually already become broken, and broken sometimes meant somebody's hand or somebody's life. So who was actually supposed to catch a problem like that before it turned into an emergency? Nobody. That was the design flaw sitting underneath the entire American system, and almost nobody had noticed it was a design flaw at all. Congress noticed the scale of that carnage before most factory owners were willing to. The Occupational Safety and Health Act, passed at the very end of 1970, built directly on the back of that death toll, and it forced American plants, for the first time, to guard their blades, log their injuries, and answer to federal inspectors. It cut the bleeding substantially, but it never touched the underlying habit. OSHA could force a company to bolt a cage around a punch press. It could not force a worker to notice a bearing running 4 degrees hotter than it should, because nobody had ever told him that noticing was part of his job in the first place. So if a federal law with real teeth couldn't fix that, what could? 10,000 kilometers away, a completely different kind of pressure was quietly building, for a completely different reason. Post-war Japan didn't have America's luxury of simply replacing a machine that broke. Steel, capital, and spare parts were scarce through the 1950s, so keeping existing equipment alive as long as possible wasn't a philosophy yet, it was survival. Preventive maintenance concepts, many of them borrowed directly from American industrial practice, started spreading through Japanese plants around that same decade for exactly that reason. Nippon Denso was an electrical parts supplier feeding Toyota's assembly lines outside Nagoya, and it became the proving ground where all of that pressure finally boiled over. In 1960, the company rolled out plant-wide preventive maintenance for the first time, assigning small pieces of upkeep to the same operators running the equipment, simply because there weren't enough dedicated maintenance men to go around. Through the rest of the decade, the company automated harder and faster still, chasing the same post-war efficiency every rebuilding Japanese manufacturer was chasing. But automation is greedy. Every new robot arm, every new automated line added more machines than the maintenance department could physically keep up with. The math stopped working entirely. Too much equipment, not nearly enough technicians, and a production schedule with 0 patience for waiting on a repair crew already stretched across half the plant. An engineer named Seiichi Nakajima, who had spent years studying maintenance systems, proposed something that read, at the time, like a demotion for the maintenance department and an unwanted promotion for the production floor. There's a strange irony buried in where Nakajima got some of his early ideas. As a younger man, he had worked as an interpreter for an American consultant touring Japan to lecture on preventive maintenance theory that had originally been developed in the United States and had never fully taken root there. Nakajima translated those American ideas into Japanese for a living, years before he ever perfected them, and handed them back across the Pacific. His proposal was straightforward on paper and radical on the shop floor. Train the operators, not to repair the machine, to know it well enough that repairs were rarely needed at all. Daily cleaning, daily inspection, learning the 4 early warnings that almost any machine gives off before it fails. Unusual heat, unusual vibration, unusual sound, unusual smell. Catch any single one of those early enough, and the failure never gets the chance to happen. Nakajima spent years refining the idea across multiple plants before Nippon Denso finally rolled it out in full. By 1971, Nippon Denso had formalized the idea across the entire plant and won Japan's first PM Excellence Award for it, a prize the country's Maintenance Institute had created specifically to recognize this new way of thinking. The approach needed a name. They called it Total Productive Maintenance. Total, because everyone in the building owned it now, not just the maintenance department. Productive, because the entire point was output, not paperwork for its own sake. Maintenance, because underneath the new name, it was still just keeping a machine alive. Done, for the first time, by far more eyes than had ever been assigned to the job before. It sounds almost too plain to be called revolutionary, a change in who is allowed to look at a machine, and when. But plain ideas travel slowly across oceans, especially when the people on the receiving end assume their own machines are already the best on Earth. So how long would it actually take American industry to swallow its pride and copy something this simple? The better part of 2 decades, and by the time it finally crossed over, the price of ignoring it had already climbed high enough to fill a cemetery in Louisiana. The man who taught the machine to talk. So what was the trick exactly? Strip away the acronyms and the consultant jargon, and total productive maintenance comes down to something almost insultingly simple. Every machine talks before it fails. It runs a little hotter. It vibrates a little differently. It makes a sound that wasn't there the week before. It starts smelling faintly of scorched grease instead of nothing at all. Every one of those signals usually shows up days, sometimes weeks, ahead of an actual breakdown. And for most of American industrial history, nobody whose job it was to notice those signals was ever standing close enough, often enough, to catch them in time. Nakajima's answer put the person closest to the machine back in charge of watching it. Every shift, before anything else happens, the operator wipes the machine down, not for tidiness, but because a rag catches the small stuff a passing glance never will. A hairline oil leak trailing down a housing, a bolt that's backed itself out 3/4 of a turn, a patch of fine metal shavings sitting where there shouldn't be any at all. Cleaning, done properly, is inspection wearing a disguise. Add a lubrication schedule the operator actually owns, instead of waiting on a maintenance work order, and a 5-minute walk-around before the shift even officially starts. And you've built something that costs almost nothing in dollars, and catches almost everything that matters. So if it was this simple, why didn't every American plant adopt it the moment the idea crossed the Pacific? Here's why that was harder to pull off than it sounds. Picture an American assembly line in the middle of the 1980s. The operator's entire job, for decades, has been speed. Hit the cycle time, hit the quota, don't touch anything you're not certified to touch. The maintenance crew's entire job, for just as long, has been ownership of the machine itself, their turf, their tools, their overtime hours. Ask the operator to start inspecting bearings and greasing fittings, and you're not simply adding a task to his day. You're rewriting who owns the machine. In a factory culture where job boundaries had been fought over, sometimes literally, for generations. Maintenance crews worried they were training themselves straight out of a job. Operators worried they were being handed extra work with none of the extra pay attached to it. Neither side was entirely wrong to feel nervous about it. What eventually broke the standoff, plant by plant, was rarely a memo from corporate. It was small, deliberately unglamorous pilot programs. One production line, one shift, a handful of volunteers willing to try the new checklist for 90 days, while everyone else watched from a safe distance to see whether it actually worked, or whether it was just another consultant's fad, destined to quietly disappear. This wasn't a technology upgrade. It was a change in who was allowed to look. Now picture the machine itself, mid-failure, so you understand exactly what that early warning was built to prevent. Every rotating shaft in an industrial plant, in a conveyor, a rolling mill, a press flywheel, an engine crankshaft, rides on a bearing, a ring of hardened steel balls or rollers packed in grease, built to let thousands of pounds spin with almost no friction at all. Starve that bearing of grease, and the friction doesn't simply disappear. It has to go somewhere. It turns into heat, right at the point of contact, climbing degree by degree with every single rotation, thousands of times a minute. Left unchecked, the bearing eventually seizes solid. If the shaft is still being driven by the rest of the machine, something has to give. A belt keeps dragging across a part that can no longer turn, grinding at one fixed point until that point gets hot enough to become an ignition source, hot enough to snap outright, or hot enough to throw sparks into whatever happens to be sitting nearby. That single mechanism sits behind more industrial fires, fatal jams, and catastrophic failures than almost any other cause on an American factory floor. And every one of them announces itself first as heat, days before it ever becomes a headline. An operator with a bare hand resting on that housing, once a shift, feels the warning long before it gets the chance to become one. Autonomous maintenance was only the foundation, but was that the whole system, on its own? Not quite. Stacked on top of it sat 7 more pillars, the Japanese Maintenance Institute eventually codified, planned maintenance scheduled around real failure data instead of guesswork, focused improvement teams hunting down the small chronic losses nobody had ever bothered to track, early equipment design that built maintainability into a machine before it ever left the drawing board, and structured training that turned that first pillar, the operator's daily watch, into an actual transferable skill. Not every American factory was starting from zero. DuPont, for one, already carried a reputation for safety and equipment discipline stretching back decades. The product of a company culture built after generations spent manufacturing something as unforgiving as explosives. But even a plant with that kind of head start still hadn't systematically handed daily inspection duties to the men running the machines, and that single missing piece was exactly what Japan had spent a decade perfecting. Remember that $40 bearing from the opening, the one that killed 7 people in Kansas. This is exactly the mechanism that was built to catch it years ahead of time. A trained hand on a housing, feeling for heat that had no business being there yet, long before any belt ever had the chance to start dragging across a frozen roller. Some plants pushed the listening even further than a bare palm. Maintenance crews at the more advanced sites started carrying handheld vibration meters, pressing a small sensor against a bearing housing to catch a change in its frequency signature weeks before a human ear or hand ever could. It was still the same underlying idea, just sharpened with an instrument. Catch the complaint early, in whatever form it showed up, before it became a failure nobody could ignore. It reached American soil in 1985 and 1986, arriving first at Tennessee Eastman, a Kodak chemical division out of Kingsport, Tennessee, and at a medical supply company called Baxter Travenol. Within a few years it had spread to 3M, DuPont, Corning, Westinghouse, Procter & Gamble, Milliken, Quaker Oats, Timken, Texas Instruments, Motorola, Exxon, General Motors, and Ford. Not one of those companies installed a single new machine to make it work. They retrained the people already standing at the ones they already had. American factories, by nearly every measure, still built bigger presses, faster mills, and heavier cranes than anything coming out of Japan. The advantage Japan had built was a different kind entirely. A refusal to waste the single most valuable sensor already sitting on every factory floor in the country. A human being who was standing there anyway, for 8 hours a day, close enough to hear the machine breathe. 5 minutes before the shift whistle. Every plant that skipped this habit was one quiet shift away from becoming Kansas, and most of them never knew it until it was too late to matter. So what did that actually look like, day to day, before anyone was watching for it. Picture the old rhythm first, so you can feel exactly what changed. It's 5:40 in the morning, at a stamping plant somewhere in the Midwest, sometime before 1985. The operator clocks in, walks over to a 600-ton press that's been running 3 shifts a day for longer than he's been alive, and does exactly one thing before the first coil of steel ever feeds through it: hits the start button. That's the whole job. Speed, not stewardship. Down the hall, a maintenance crew of 2 or 3 men sits in a windowless room with coffee and a thermos, waiting for the phone to ring, because that's their entire job too. Not prevention, response. When it rings, it's rarely good news. A press jammed mid-stroke with a die half-formed inside it. A conveyor motor locked solid and already smoking. A crane cable frayed down to half its rated strands that nobody caught until it groaned on the very last lift of the shift. The maintenance men become something closer to firefighters, sprinting from one small blaze to the next, cannibalizing a working part off one idle machine just to keep a critical one limping along, because ordering the actual replacement part through the proper channels takes 6 weeks, and the floor doesn't have 6 weeks to spare. Whole graveyards of dead equipment pile up in the back corners of plants from this era. Engines and gearboxes stripped down to nothing, kept around purely as organ donors for the machines still limping through their shifts. Call it a controlled emergency that never quite stops being an emergency. Day after day, year after year, and every single emergency carries the same risk: a crushed hand, a burned arm, a body in the wrong place when something finally lets go. How long could a plant actually run like that before the odds caught up with somebody on the floor? Now picture that same 5:40 in the morning, a decade or two later, inside a plant that finally adopted the Japanese approach. You clock in, and before that first coil ever moves, you're already circling your own machine with a rag in one hand. You wipe down the guardrails, not because anyone's inspecting for dust, but because a clean surface will show you a fresh oil stain in about half a second, while a dirty one hides that same stain for a month. You crouch by the bearing housing on the drive shaft and rest your palm against it for 3 full seconds, feeling for a warmth that shouldn't be there yet. You check the sight glass on the lubrication reservoir against a line somebody painted on it in grease pencil years ago. You listen, really listen, for the particular hum this exact machine makes when everything is right, because you've heard that hum 10,000 times, and you'd know inside half a second if it ever changed. If something feels off, you don't call anyone yet. You write it on a tag and hang it exactly where the next shift will see it first, so their eyes inherit your suspicion instead of starting from nothing. Walk down the same plant, and you'd see the same ritual wearing different clothes. The crane operator climbs into the cab 20 minutes early now, not 5, running the hook block up and down empty before a single load ever gets rigged, watching the cable feed onto the drum for a strand that's starting to fray, before it becomes the one that snaps mid-lift. The man running the grain conveyors starts his morning laying a bare hand against every accessible bearing housing along the line, one after another, because he's been told exactly what happened in Kansas and exactly how little it would have taken to stop it. None of that takes more than 5 minutes. None of it requires an engineering degree. All of it requires believing that watching the machine is your job now, and not somebody else's down the hall, and that belief, more than any grease gun or checklist, was the actual invention. Did operators actually want any of this the first time someone asked them to do it? Almost none of them did. It didn't arrive easily. Plant after plant across the American Midwest and South spent the late 1980s working through real friction on both sides of this change. Maintenance departments, built for generations around the idea that only a licensed technician touched a bearing, watched their headcount projections shrink, and quietly wondered whether they were training their own replacements. Production operators, paid and graded purely on units per hour, wondered aloud why they were suddenly being handed unpaid extra duties that used to belong to somebody else's paycheck entirely. Union contracts in plenty of plants had literally drawn lines around who was allowed to touch which piece of equipment. A millwright's job classification protected by decades of bargaining, a production operator's classification kept just as carefully separate. And those lines didn't dissolve simply because a consultant flew in from Japan with a slideshow and a translator. Getting an operator to legally, contractually lay a hand on a bearing housing sometimes took new language in the next labor agreement, not just a new training manual. What actually moved the needle, plant by plant, was never a mandate handed down from a corner office. It was operators discovering, one caught bearing at a time, that a 5-minute routine they'd resented at first was quietly saving somebody's worst hour of the year, theirs, or the next man's on the following shift. Word of a near miss caught early traveled fast on a factory floor, faster than any memo from management ever could, because it was the kind of story men told each other over lunch. The bearing that felt just slightly warm on a Tuesday, the tag that got hung, the disaster that never happened because of it. Pride turned out to be a strange kind of lever. Once an operator caught his first failure, before it ever became a disaster, he rarely wanted to go back to being the man who just pushed a button and waited on a phone call from down the hall. The morning, the silos came down. 2 mornings explain what a missed bearing check actually costs in human bodies, better than any statistic in this video could on its own. The first one is December 22, 1977, at the Continental Grain Company elevator in West Wego, Louisiana, a few miles up the Mississippi from New Orleans. It's 3 days before Christmas. Company tradition that year includes handing out turkeys to employees, and some workers who aren't even scheduled that morning have stopped by anyway, on their day off, to collect theirs and trade a few words with friends before the holiday. A ship is being loaded at the dock nearby. Deep inside the 250-foot concrete tower and the maze of tunnels underneath it, fine grain dust, a natural byproduct of moving hundreds of thousands of bushels of corn, has been quietly accumulating in places nobody had been cleaning as carefully as they should have. Somewhere in that dust, an ignition source nobody would ever conclusively identify sets it alight. The blast tears through the structure just before noon. 43 silo tops get blown off like bottle caps in a single instant. The shockwave rolls backward down the entire line of towers, shattering concrete as it goes, and the head house folds sideways directly onto the 2-story cinder block office building next to it, the very building where the Christmas turkeys were being handed out, where the day's paperwork was being filed, where people stood who had no reason to believe that particular morning was different from 100 mornings before it. A witness who watched it from the riverbank later described a fireball climbing 100 feet into the sky, followed by a cloud of grain and pulverized concrete drifting out low over the water, where ducks paddled through the scattered kernels as if nothing at all had happened 40 feet away. Investigators would eventually put the direct property loss alone at around $30 million, on top of everything else. A local reporter walking the grounds that afternoon said the wreckage looked like a block out of a bombed European city at the end of the Second World War. Rescue crews dig for over a week straight. The death toll climbs almost daily in the local paper, like a countdown running the wrong direction. 10 confirmed by early afternoon, 15 by the next day, 25 once somebody remembers a crew of construction workers who had gone inside early that morning, and searchers finally locate them. By Christmas Day, the headline reads that the ruins have yielded a 33rd body. Firefighters spend the holiday itself dynamiting through rubble, looking for the rest. Jefferson Parish's sheriff, working the scene without sleep, tells a Wire reporter simply, "It's almost more than we can bear." By New Year's, the number stops climbing at 36. It remains the deadliest grain dust explosion in American history. West Wego wasn't even the only grain elevator to explode that particular December. Within the same brutal week, blasts tore through elevators in Wayne City, Illinois, killing 1, in Tupelo, Mississippi, killing 2, and in Galveston, Texas, killing 14 more. An entire American industry lost dozens of workers to the same basic hazard inside a single month. And almost nobody outside the grain trade noticed the pattern until the death toll from Louisiana forced the country to look. Nobody could prove, in the end, exactly which spark started the Westwego blast specifically. But the investigators who spent 1978 studying it, along with dozens of smaller elevator explosions across the country, that same brutal winter, kept landing on the same short list of usual suspects, over and over. Welding sparks, faulty wiring, and, high on nearly every list, bearings that had been allowed to run dry, overheat, and throw off exactly the kind of friction spark that a room full of suspended grain dust never forgives. In the years right after, the town of Westwego went quiet, the way small places do after something enormous happens to them. Families buried their own. The company rebuilt on the same stretch of riverbank, because the grain still had to move, the ships still had to be loaded, and the work, in the end, always finds its way back to the water. Life along that bend of the Mississippi kept going, the way it always does, just with 36 fewer people in it than it should have had. Did the rest of the grain industry actually learn anything from it? Some of it did. Some of it took another 21 years and 7 more bodies to learn the exact same lesson twice. That's the first morning. The second one happens 21 years later, and this time, investigators know precisely what went wrong, down to the temperature. June 8, 1998, Hayesville, Kansas. DeBruce Grain. Deep in the east tunnel beneath the south row of silos, a roller bearing on a piece of equipment called a concentrator has run dry, starved of a lubrication schedule that should have caught the problem days or weeks earlier. The bearing seizes solid, but the conveyor belt above it doesn't stop. It keeps running at more than 8 miles an hour, dragging itself across a roller that can no longer turn, over and over, thousands of times a minute. Investigators would later call it the razor strop effect. Friction drives the frozen roller's temperature up to nearly 500 degrees Fahrenheit, well past the point at which layered grain dust ignites on its own. Workers on shift that week had already reported one small fire in that exact tunnel, in that exact spot, about a week earlier. Nobody had traced it back to its source in time to stop what came next. When the dust ignites, it doesn't stay a single explosion. It sets off a chain of secondary blasts of growing size as the shockwave stirs up more suspended dust deeper in the tunnels and silos. 7 people are killed. 10 more are hurt, badly enough to be hospitalized. It would later come out that this same elevator had already lost 2 workers years earlier, in 1978 and 1983, during separate confined space rescue attempts that had gone wrong. A facility, in other words, with its own long and quiet history of close calls that had never once forced its culture to change. Federal investigators spent months afterward reconstructing the sequence down to the individual roller, and the case became one of the defining studies the agency still points to today, whenever it teaches plant managers what a single deferred lubrication task can cascade into. Sit with the arithmetic of that second morning for a moment, because it is the entire argument of this video compressed into a single fact. Could anyone have stopped it? By 1998, the honest answer is yes, easily, and everyone in this industry already had the tool to do it. Total productive maintenance had already been running successfully in American plants for 13 years. Tennessee Eastman had it. General Motors had it. DuPont had it. The exact habit that would have caught a dry, overheating bearing, a hand resting on the housing, a lubrication schedule somebody actually owned, a tag hung the instant something felt wrong, was not a secret by then. It was documented, published, and taught in plant after plant across the country. It simply hadn't reached this particular elevator in this particular small Kansas town in time. 7 people did not get to go home that June, for the same reason 36 people didn't get to open their Christmas turkeys 21 years earlier, because the person standing closest to the machine had never been asked, trained or trusted to notice that it was already trying to tell him something, in the only language a machine has ever known how to speak. What the beast learned to confess. West Wego forced a reckoning the grain industry couldn't quietly file away and forget. In the summer of 1978, scientists and engineers gathered in Washington for an international symposium built specifically around grain elevator explosions, trying to answer a question that had already cost dozens of lives that single winter alone. A researcher on the National Academy of Sciences panel, a scientist named Robert Shane, put the underlying problem about as plainly as it has ever been put. You can't always keep all bearings from drying out and overheating. His conclusion wasn't that every ignition source could somehow be eliminated one by one. People would always weld, always strike a match, always let a bearing run a little longer than they should. His conclusion was that the industry had been fighting the wrong half of the equation. Nobody could guarantee catching every spark. What could be controlled was the dust that turned a spark into a catastrophe, and the eyes watching the machines that kept producing sparks in the first place. New regulations followed within a few years. Heat sensors on rollers and bearings built to catch precisely the kind of failure that would still kill 7 people in Kansas 2 decades later. Isolated headhouses, so an explosion in the tower could no longer collapse onto an office full of employees collecting their Christmas turkeys. And dust control standards that treated housekeeping as an actual safety system rather than a chore somebody got around to eventually. The same year OSHA was created, Washington also stood up the Mine Safety and Health Administration to police an entirely different set of machines running on the same run-to-failure habits, underground rather than under a factory roof. And the two agencies together spent the following decades slowly dragging American heavy industry toward a culture that measured equipment condition instead of just waiting to discover it the hard way. Outside the grain industry, did any of this actually spread, or was Kansas just one unlucky town that never got the memo? It spread, and the numbers say so plainly. The broader adoption of total productive maintenance kept compounding through the 1990s and into the new century. Longitudinal studies tracking American automotive plants that implemented it properly found unplanned downtime falling by roughly a quarter in the very first year alone, more than half by the third year, and around 70% by the fifth, without a single new machine ever hitting the floor, purely from operators catching what used to go uncaught entirely. Plants that had spent decades limping along at 40 to 60% overall equipment effectiveness started closing in on the 85% mark the industry now considers world-class. Later surveys tracking these same plants years afterward found the great majority, somewhere around 84% of them, had held on to those gains or improved on them further. Proof that this was never a one-time consultant fad that faded once the slideshow was packed away. None of that came from bigger presses or stronger steel. All of it came from a bearing getting a hand laid on it once a shift, by somebody trained to know exactly what 4 degrees too hot actually felt like against his palm. The country that had once measured its industrial might purely in tonnage and horsepower had quietly started measuring it a second way as well. How rarely a machine was allowed to surprise the person standing beside it. Look at where all of this sits today, and the machines themselves haven't gotten any less dangerous in the meantime. A modern stamping press can still take a hand off in less time than it takes to finish reading this sentence. A rolling mill still runs hot enough to cook a body if somebody were foolish enough to touch it wrong. What's different is who's watching, and how early. Autonomous maintenance, folded now into the broader language of lean manufacturing, is standard practice across American auto plants, chemical plants, food processing lines, and heavy industry generally. So ordinary decades later that most new hires are never even told it was once considered a foreign import. They're simply trained, from their very first day on the floor, that the machine is partly theirs to watch, the same way a pilot is trained to walk around the plane before ever touching the throttle. Walk a modern American plant floor today, one that actually took this seriously, and the difference isn't loud. It's quiet in a way the old floors never were. Fewer sirens, fewer unscheduled shutdowns, a maintenance department that spends its mornings reading printouts of vibration trends instead of sprinting toward smoke. An operator who can tell you, off the top of his head, exactly how many degrees hotter his machine is running than it was last Tuesday, because checking that number became as automatic as checking his mirrors on the drive-in. OSHA's own numbers close the loop better than any closing line could invent on its own. That worker dying every 38 minutes back in 1970 has become, by the most recent counts, a worker dying roughly every 96 minutes. Still too many, still a number this industry keeps grinding away at, but less than half of what it once was, across a workforce that's nearly doubled in size since anyone started counting. So is the trick still working, decades after it stopped being a secret at all? Walk any serious American plant floor today, and the answer is standing right next to the machine, rag in hand. The beast got tamed the only way something that size can ever be tamed at all, through a hand resting on a bearing housing once a shift, trained to notice 4 degrees of difference long before it ever had the chance to matter. They still build machines that big in this country. They just don't run them blind anymore. Not since somebody finally taught the man standing next to the beast that his job was to listen for it breathing wrong, long before it ever got the chance to scream.